Let's go fast and slow reactions. Where's my cursor? There we go. And get my laser pointer. Cool. Key knowledge. Chemical reactions with reference to collision theory, including qualitative interpretations of what's called the Maxwell-Boltzmann distribution curve. You may or may not have heard of that. So qualitative, right? So not quantitative reactions. Comparison of exothermic and endothermic reactions, including their enthalpy changes and representations in energy profile diagrams. We've seen them before. Factors affecting the rate of the chemical reactions, including temperature, surface area, concentration, gas pressure, and presence of a catalyst. So if we take a page, divide it into 4, right? Divide a page into 4, and what we want to do is factors affecting rate of reaction. Our first column is going to be each of those 4 factors, right? So surface area is our first factor. Second factor, concentration. And what I'm actually going to do is I'm going to include gas pressure in this same quadrant. Because an increase in gas pressure is actually increasing the concentration of gas, right? We think about what concentration is. It's amount of substance in a given volume. If I increase the pressure, I'm increasing the amount of gas particles in that given volume, right? So our reasoning for how it affects using collision theory is exactly the same. So concentration of solutions, gas pressures, temperature, right, and catalysts. I've already spoken a bit about catalysts. Well, I've mentioned it in passing. Temperature, concentration, and gas pressure. 4 factors. The role of catalysts in changing the rate of chemical reaction with reference to alternative reaction pathways and their representation, again, in energy profile diagrams. Learning intention, describe the energy changes, blah, 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 blah. I won't go through all of those, word for word. Okay, energy profile diagrams. Seen these before, yeah? Chapter 2, energy. So, if we have input energy into the system, right, endothermic. System becomes warmer. It feels cold because it's absorbing the heat from your hands. Heat released, right? All combustion reactions are exothermic reactions. The energy of the product is lower than that of the reactants. We've seen this before, right? The general energy profile diagram of exothermic and endothermic reactions. Comparatively speaking, activation energy of an endothermic reaction is higher than that of an exothermic reaction for a similar reaction, right? Or the reverse of one. Delta H in exothermic is negative. Yeah, delta H in endothermic is positive. Shut that down. Okay, this is called a Maxwell-Boltzmann distribution curve. I'm going to relate it predominantly when talking about catalyst and temperature. So let's look at that first. It's called what I call an MBD, Maxwell-Boltzmann distribution. I don't really need to know what it's called, but we need to know how to look at it and how to interpret it. So what I've got is, we've seen different distributions. What does the word distribution mean? Yeah, how spread out something is. Where have we seen distribution before? In maths. Where in maths? Right. So we're talking about sample of people. Yeah. And this is what do I call this? This is energy. So we've got a sample of people. Yeah. And so let's consider, right, just for a moment, you don't have to draw this down. Imagine this is pieces of toast, Yeah? And how much Vegemite do you like? Do you like none? Hands up. Okay, one. The finest scraping of Vegemite. Any more? For argument's sake, right? 2, cool. You want just a bit of Vegemite, yeah? Cool, awesome. 1, 2, 3, 4, 5. Cool, fantastic. You absolutely love to slather your toast with Vegemite. 1, cool. We've just generated a Maxwell Boltzmann distribution curve, right? The number of particles, the number of students, and the quantity of Vegemite on your piece of toast. And we find we've got this distribution. 1, 2, large amounts, back down to slather, right? Yeah. Now if I replace the Vegemite, let's say, with jam, who likes no jam? So none, cool. Just the finest scraping of jam. Okay, none there. Reasonable amount of jam. Yeah, cool. 1, 2, 3, 4, 5. Cool. 6, 7. Slather it with jam. Cool. Then we've got 4. Cool. Fantastic. So what we've done is I've now shifted the distribution. Have I changed the number of students in the class? No. So the total number of students don't change. But I've shifted the distribution into something that you like better. Yeah? We can do the same with energy because temperature and energy are somewhat related, right? A higher temperature of something means it's got greater amounts of kinetic energy. Yeah? Make sense? So I've got this distribution of particles. The total number of particles don't change. So I'm going to call this temperature 1. And as I increase the temperature, I shift the distribution. I call this temperature 2. Total number of particles hasn't changed. Let's say I've got the sealed vessel, total number of gas particles in here hasn't changed. I've just turned up the heating. So as I've increased the temperature, I've increased the proportion of particles traveling at a higher velocity or higher energy. Does that make sense? Yeah? What 2 things must we have in order for a reaction to take place? Contact. What do you mean by that? Yeah, you must be touching one another. Let's look at this high five example. Right, give me a high five. Did I have a successful high five? Yes. According to you, yes. All right. No, I didn't. So give me a successful high five. Right, so orientation must be right. Yeah? So that's 1. Orientation. What's the other thing we need for a reaction to be successful? Give me a high five. Pathetic, isn't it? What do we need? Yes, that's what we need, right? What did I change? The energy. So we need our 2 things. We need our orientation. We don't hear anything if the energy isn't enough. We don't have a successful high five. So I get a nice bit of energy. I get that nice pop clap sound. Yeah? So sufficient energy. What do we call that? Activation energy. Fantastic. Right. So activation energy and orientation. So I've got activation energy here. So at a when I increase the kinetic energy of all the particles, a greater amount of particles are traveling above the activation energy. Make sense? So, more particles traveling at a higher kinetic energy results in greater number of collisions, yeah? Which therefore means that if I've got a greater number of collisions, then the number of those that are going to be successful will also increase. That make sense? Because we're talking about rate, what does rate mean? The amount compared to time, right? So, yeah, the amount. So we've got to talk about the amount related to time. What might we refer that to? There's a singular word when we refer to something over time. If I hit you once every second versus twice every second, what do we call that? Frequency. Yeah. So, as I increase the temperature, I increase the proportion of particles traveling above the activation energy. Yeah. Increases the number of collisions. That increases the frequency of successful collisions. That therefore increases the rate of reaction. With me? So let's go through that. As I increase temperature, I increase the kinetic energy of the particles. Yeah? That increases the proportion of particles above the activation energy. Yeah? Increases the frequency of successful collisions. That therefore increases the rate of reaction. That's my shorthand. Yes, question?
You're saying that you're only looking at the successful collisions. Does that mean that in a certain reaction you could have the two reactions bump into each other and just bounce off?
Exactly right. Yeah? So, let's do an analogy. Everyone stand up. Go back to, I'll do catalyst later. Oh, I haven't finished off this presentation. Okay. I'll come back to this. I'll just pause that. So